Good afternoon. I welcome you to this discussion on steam and gas turbines. This is essentially the continuation of what we have discussed in the last class. In the last class, as you can recollect, that we have talked about the construction of the steam and gas turbines, in particular the steam turbines, and now we will talk about their performance. So, to understand this, we will take resort to the velocity triangles that we have already discussed in the earlier part of this module, and then we will apply it for the case of steam turbines. Of course, you have to keep in mind what I talked about in the last class, that we are talking about the steam as like a superheated steam and not really talking about the wet phase. So, we will talk about the HS plots and connect the two, and most importantly we will talk about the degree of reaction or the reaction ratio. Now, we will define few terminologies which will help us to also understand these turbines and solve the problems that we have given in the tutorials. The first is the nozzle efficiency. We have already talked about that the nozzle has a higher pressure, higher enthalpy at the inlet, and after the expansion the enthalpy and the pressure should drop. And if you recollect our terminology, we have said higher the value of pressure or enthalpy, we will give a higher number. So, in this case, if you remember the simple impulse turbine, for example, we have first the nozzle and then the rotor. So, if I start from the rotor exit as 1, then rotor inlet becomes 2, which is also nothing but the nozzle exit. So, the nozzle inlet should have a number 3. So, please note that these numbers 3, 2 may differ in different books, but we are following the unified notation that we have discussed towards the beginning of these lectures on turbo machine. So, 3 to 2 is an expansion process and 3 to 2s is an idealized process, where 2s refers to the isentropic expansion. 03 corresponds to the total pressure, P03 corresponds to total pressure and 03 corresponds to the stagnation state, and 02 corresponds to the stagnation state at the exit of the nozzle. The corresponding pressure, please note, is P02. In the last lecture on compressible flows, this aspect we have already discussed. We have shown that H03 should be equal to H02. Why is that? You recollect that nozzle does no work and there is no heat transfer. So, from the first law of thermodynamics, neglecting potential energy changes, we can say that H03 is equal to H02. But what about pressure? That also we have discussed in the last lecture, that P03 is not equal to P02 and there is a pressure drop to overcome the friction. So, this is depicted here, and that brings to us the concept of nozzle efficiency, and we can say that nozzle efficiency eta n is given as C2 square by 2 divided by C2s square by 2. What we are essentially saying is this velocity, that is which takes from here to here as the actual velocity in that is obtained at the exit of the nozzle, to the ideal velocity that you can get from the exit of the nozzle. And of course, we know that ideal velocity is obtained if we say that from the isentropic expansion, and delta H isentropic or delta H isen refers to the total drop in enthalpy from the state 03 to 2s. So, eta n then can be represented as C2 square by C2s square or C2 square by 2 delta H isen. Alternately, it can also be expressed in terms of loss coefficient zeta n or velocity coefficient. The nozzle velocity coefficient, for example, we have discussed also in case of Pelton turbine. So, we can say zeta n is nothing but H2 minus H2s, the loss in enthalpy, divided by C2 square, the what fraction of it is lost, and then we can also define the velocity coefficient as C2 by C2s. If you manipulate with these terms, and I would urge you to do it yourself, show that eta n is equal to k n square, of course, this is obvious, is equal to 1 whole divided by 1 plus zeta n. So, eta n equal to k n square equal to 1 divided by 1 plus zeta n, and this is the way of expressing the nozzle efficiency. So, let us look at the velocity triangle for an impulse turbine stage. So, this is an impulse turbine stage and we are talking about the velocity triangle. So, the velocity that enters here is C3, which is at the inlet of the nozzle, leaves with an absolute velocity C2. You see that C3 has increased by several orders, which is expected because nozzle is supposed to increase it. Then you know the pressure and the suction surfaces, we can get the direction of rotation as shown here. We can construct the velocity triangle at the inlet of the rotor and similarly at the exit of the rotor. And you can also once again verify that had there been no blade, rotor blade, the velocity would have continued in the direction of W2, but now it is forced to go in a W1 and hence the deflection angle is large. So, let us draw the velocity triangles together. When we talk about axial flow turbines, many times what we do, we take advantage of the fact that this blade velocity, blade peripheral velocity u is same at the rotor inlet and outlet, and we can draw it in terms of common base. So, this u serves as a common base and a direct method of comparing the inlet and outlet velocity triangles. We can mark C2u and C1u, and please note that we had earlier written when we talked about Euler's energy equation or Euler's turbine equation that it is C2u minus C1u, but that is because they were on the same side. Now, if you look at this graphical representation, you can see that C2u is on one side and C1u is on the other side. So, what we are essentially trying to do is find out the distance between this tip and the other one. So, we are essentially trying to talk about the summation of the total distance C2u and C1u. So, in case they are on the same side, then what will happen is it is going to be C2u minus C1u. In this case, it will be C2u minus of minus C1u, because C1u is on the opposite side. This has to be borne in mind when we follow this discussion today. So, let us look at it. We are talking about C2u as u plus W2u and C1u is W1u minus u, and hence neglecting friction where we can consider the W1 equal to W2, the same as we have done in case of Pelton turbine. We can find out that pi minus beta 2 is beta 1. I will come back to this point again, and this is known as symmetric blading. Please note the relationship that pi minus beta 2 is beta 1. This is valid because of the nomenclature that we have used, the sign convention of beta we have used. You can get a similar symmetric blading conditions in other way if you use some other way of denoting the blade angles. But for the way we have denoted the blade angle, that is blade angle in our case is denoted by the angle between the positive direction of W. For example, let us say I am talking about positive direction of W and the negative direction of u, which is this angle. So, this angle is my beta, which means the vertically opposite angle. This also should be my beta. So, this should be my beta 2. So, please note that this is the sign convention we have used, and hence because of this sign convention the symmetric blading condition gives me pi minus beta 2 equal to beta 1. If you had followed, I repeat, if you had followed any other convention of the blade angles, then this relationship will be changed, but still you should get the symmetric blading, because that is important, because velocity triangles here we are talking about is the same, the angle representation is different. So, we can look at the HS plot for a turbine stage. So, 3 to 2 is an expansion in the nozzle, 2 to 1 is the expansion in the rotor, and we are talking about 3 to 2s, as the isentropic expansion in the nozzle, and 2 to 1 s is the isentropic expansion in the rotor, and 1 s talks about the isentropic expansion from 3 at the pressure P 3 to the pressure P 1. We can also write that this is P 02 and this pressure line is corresponds to P 03. So, H 03 should be equal to H 02 as we have discussed, and then this distance is the velocity rise, which is half C 2 square. We can also show that this pressure is called P 02 relative. Please note the distinction between P 02 and P 02 relative. When I say P 02, I mean P 2 plus half, basically it is connected with C 2 square. We cannot write with half rho C 2 square, I am sorry, we cannot write it, but we have to connect it with C 2 square. For example, I can write that T 02 is equal to T 2 plus C 2 square by 2 C p, and we can connect the pressure also using the relationship we have derived earlier in terms of Mach number. Now, P 02 relative is connected with the velocity of W 2 instead of C 2. Similarly, P 01 relative is connected with the velocity W 1, relative velocity W 1 instead of C 1, whereas P 01 is connected with the absolute velocity C 1. So, let us look at it again. P 1 and P 01 is connected with the absolute velocity at the exit of the rotor C 1. P 01 relative is the stagnation pressure based on the relative velocity condition, and that is given related with W 1 square. Similarly, with P 02 and P 02 relative. So, now velocity triangle for a turbine stage. If I look at the velocity triangle for a turbine stage, which we have already drawn in the last time, we can get that H 02 relative equal to H 01 relative. I am not showing it in today's lecture. I will give a separate handout, but I suggest that you first derive it yourself. If you are really not in a position to do it, then you look at the handout and then we can have the discussion if required. But please try to prove that for the condition given H 02 relative equal to H 01 relative. I have already shown it of course by this horizontal line. So, some more definitions we need. We can talk about the blade efficiency eta BL as WBL by C 2 square by 2. What it is saying? That how much specific work is obtained from the blade when the kinetic energy input is C 2 square. So, that means how much of the kinetic energy that is being converted into useful blade specific work, and this is exactly the same what we have talked about in case of Pelton turbine. Please keep the similarity between the Pelton turbine definitions and the steam turbine. Exact expressions will little bit vary, but the philosophy is same. In case of Pelton turbine, we talked about the jet velocity C j, which is our C 2, which comes out with a high kinetic energy. In this case, the steam comes out of the nozzle with C 2 square by 2 as a kinetic energy per unit mass. So, we can write now 2 u C 2 u plus C 1 u. I again re-emphasize this point that you can think about this C 2 u plus C 1 u in this way. You can say that C 2 u minus of minus C 1 u. So, this is what I am saying, C 2 u minus of minus C 1 u. This second minus inside the bracket actually denotes that C 1 u is in the direction opposite to C 2 u, and we are talking about the distance, total distance in the graphical scheme. So, we can say that C 2 u plus C 1 u by C 2 square. Again, to remind you, we are talking about this distance, that from this part, from this tip of u, we are going in the left side to get C 2 u, and we are going on the right side to get C 1 u, and hence the total distance is C 2 u plus C 1 u. This has to be borne in mind. and we should not use just C2u minus C1u without having the velocity triangle. In fact, let me also stress at this point that whenever you are solving problems where we need to find out velocity or the blade angles, it is always a good habit to draw the velocity triangle as accurately as you can and then work it out. That will always give you the confidence that your values are becoming realistic. So, next definition that we need to know is the normal stage definition. See, we are talking about multiple stages of a steam or gas turbine. So, in this case the normal stage is one in which the absolute velocities and flow angles in stator at the entry and exit of the stage are identical. That is C3 is equal to C1 and alpha 3 is equal to alpha 1. Why do we need such a normal stage definition? That is because the flow that leaves from one stage actually goes to the next stage. So, if we are trying to talk about the similar constructions, then we are saying that C3 is equal to C1 and alpha 3 is equal to alpha 1. So, unless otherwise mentioned, we can always assume that this is the normal stage assumption is valid. The next thing is our total to total efficiency. We have talked about the total to total efficiency earlier also, and we have told that time that total to total efficiency is nothing but H03 minus H01 divided by H03 minus H01 SS. Please recollect that H03 minus H01 SS is a isentropic isentropic process by which the enthalpy drop is calculated, and then H03 minus H01 is the actual process. Similar to nozzle loss coefficient zeta n, we can also define rotor loss coefficient zeta r as follows. We can say that if zeta n is nothing but H2 minus H2s by C2 square by 2, then zeta r will be H1 minus H1s. H1 minus H1s is actually reflecting how much of the enthalpy is lost, and then divided by the corresponding velocity in case the rotor is rotating. So, we can talk in terms of the relative velocity W1 square by 2, which comes out of the rotor exit. And if we further assume that C1 SS is almost equal to C1, you know that they are not exactly same. Why? Because densities are not same, and if we have to say the same mass flow rate as we have discussed earlier, then C1 S is not equal to C1. But if we assume that the variation between C1 SS and C1, the difference between C1 SS and C1 is not significant, then we can say that eta Tt is can be given as 1 plus zeta r times W1 square plus zeta n times C2 square multiplied by T1 by T2 whole divided by 2 H3 minus H1 to the power minus 1. You can prove this. I will also leave this in the handout, but you try to do it yourself, and I am giving you few hints. You can use the relationship that del H del S at constant pressure is T, and then using that relationship you can write that H1S minus H1SS is equal to T1 times S1S minus S1SS, and H2 minus H2S is T2 times S2 minus S2S. That is coming directly from this relationship, and once you use the definitions of zeta r, zeta n, you should be able to get an expression of total efficiency in terms of zeta r and zeta n. And as you can see that this relationship will require a little bit of manipulation of the expressions you have given. So, I leave it for you to prove it. I will also give you a handout which you can refer. I would suggest only if you are not able to do it yourself. Try it out. I hope you will be able to derive it. So, the next thing that we have to talk about is degree of reaction, or sometimes called reaction ratio in different textbooks and literature of a turbine stage. We know that R equal to degree of reaction is equal to H2 minus H1 divided by H3 minus H1, and for a normal stage we know that C3 equal to C1, just now we have talked about it. So, we can add in the all the terms the C3 and C1 respectively, and then we can write that R equal to H2 minus H1 whole divided by H03 minus H01. What we have done? We have written H03 as H3 plus C3 square by 2 and H1 as H01 as H1 plus C1 square by 2, and since C3 and C1 are same, so H3 minus H1 is equal to H03 minus H01, and we can write R equal to H2 minus H1 by H02 minus H01. How can we write it? Because H03 is equal to H02. We have already shown that in the nozzle the stagnation enthalpy remains constant. We also know that H02 relative is H01 relative. I am giving it in red to remind you that you have to prove it, and then we get that H2 minus H1 is half W1 square minus W2 square. That is, I can write H02 relative as H2 plus half W2 square, and H1 plus half W1 square will give me H01 relative. If I write the H2 minus H1, because that is in the numerator in terms of the velocity differences or the kinetic energy differences, then H2 minus H1 can be related with W1 and W2. So, we can also know that WBL is U times C2U plus C1U, which gives me H03 minus H01, and which is nothing but H02 minus H01. So, now we have an expression for H02 minus H01 as well as H2 minus H1 in terms of the velocity components, and we can write in either way R, that is in terms of the enthalpies or in terms of the velocities, and we can write that W1 square minus W2 square by 2U times C2U plus C1U. Let us look at the velocity triangle once again, and we can say that if C1m equal to C2m, if we make this further assumption, then we should be able to say that W1 square minus W2 square can be written as W1u minus W2u multiplied by C1u plus C2u. How do you get it? Let us look at how you get this. You can write, for example, W2 square equal to C1m square plus W2u square, and W1 square as C1m square, because I have assumed that C1m equal to C2m plus W1 u square. So, if you subtract it out, what you get it is W1 square minus W2 square will be W1 u plus W2 u multiplied by W1 u minus W2 u. So, now what happens is, this is we obtain. So, what happens is, now W1 u minus W2 u is nothing but we are talking about this distance. We are talking about this distance, which is exactly same as C1 u plus C2 u. We are essentially talking about, let me mark it, this distance. So, this distance is nothing but W1 u, this much is W1 u, and this is this much is W2 u, and this one is W1 u. You can alternatively think that this one is C2 u and this portion is C1 u. That is, you can say it either in terms of W2 u and W1 u, or you can say this portion is C2 u and this portion is C1 u. So, I guess you now understand that what is the reason behind this derivation. So, you see that W1 square minus W2 square is W1 u minus W2 u times W1 u plus W2 u, and W1 u plus W2 u is nothing but C1 u plus C2 u. So, we can say that the degree of reaction R then becomes W1 u minus W2 u whole divided by 2 u. So, if we continue the discussion further on the degree of reaction, and we can write that W1U is Cm cot beta 1. So, W1U is Cm cot beta 1 and W2U is Cm cot pi minus beta 2, because my beta 2 is this angle and hence we are talking about this angle which is pi minus beta 2 or minus Cm cot beta 2. So, I can write also in terms of the blade angles, and hence I can write that R equal to Cm times cot beta 1 plus cot beta 2 whole divided by 2u. And now let us take some special cases. Let us say R equal to 0, which means the numerator has to be 0. Now, Cm cannot be 0 because in that case there is no mass flow rate. If there is no mass flow rate, then there is no question of the turbine performance. So, the only way R can be 0 if is this bracketed term is 0, which means that beta 1 is pi minus beta 2. So, we see that in case of the impulse turbine R equal to 0, we get back the symmetric blade condition which we have already discussed earlier. So, we get back and you can draw the velocity triangle which you have discussed earlier. Now, let us look at two cases of R equal to 0, one with friction and other without friction. Let us start without friction. So, in case of without friction, we see that the expansion takes place in the nozzle from 3 to 2. Since R equal to 0, we know that H2 equal to H1 and there is no pressure drop. So, 2 and 1 becomes coincident points. In case of the frictional case, we know that the pressures cannot be same. However, R equal to 0 forces me to say that H2 equal to H1. So, 3 to 2 is an expansion in the nozzle, then this is the horizontal line and this point is your point 1. So, what we find that there is an entropy increase because there is a friction and the pressure has reduced. So, in this case, strictly speaking, even though we get R equal to 0 from the enthalpy definitions, there is a pressure change. And if we consider that if we want to insist that we want an impulse stage, that is we want the pressure not to change, then what happens? That 2 and 1, the points 2 and 1 should lie on the same pressure curve. So, in that case what happens is 3 to 2 is an expansion in the nozzle and then it goes from 2 to 1 because there will be an increase in entropy because friction is present, and we find that H1 has become more than H2. Recollect what is the definition of R. Let us go back and write the see the definition of R once again. We will see that R is H2 minus H1. Now, in the case of friction and impulse stage, we find that in the case of friction with impulse stage, we find that H1 is more than H2, which means H2 minus H1 is negative. So, what happens to the degree of reaction? You can find out now. So, it is actually going to be negative. So, let us try to get these points back in our mind again. So, first is when we say R equal to 0, in the idealized case of no friction, there is no issues, because points 2 and 1 are coincident points. So, H2 minus H1 is 0, the pressure is there is no pressure drop, P2 equal to P1. The moment we insist that R is equal to 0 and there is friction, then what happens? The pressure should drop, though enthalpy should remain same. So, H2 is equal to H1 is honored, but not pressure P2 equal to P1. So, in that case we find that strictly speaking definition of impulse stage, that is no pressure drop, is not valid. Whereas, if we want to insist that there is no pressure drop, but there is friction, then we find the degree of reaction becomes negative. So, this has to be kept in mind, and another important special case that I will consider now is R equal to 0.5. So, I can write in the same way that W1U equal to Cm cot beta 1 is equal to u plus Cm cot pi minus alpha 1, and W2U is Cm cot pi minus beta 2 is equal to minus Cm cot beta 2, and I can write it in terms of Cm cot alpha 2 and u. So, basically I am trying to use the blade angles, which is beta 1 and beta 2, and the nozzle directed angles of the absolute velocities alpha 1 and alpha 2. So, then if I write W 1 u minus W 2 u, I can get an expression in terms of the velocities u and Cm and alpha and beta. So, we get it that Cm cot beta 1, which we get from here, minus Cm cot alpha 2 plus u. Why am I getting it? Because I am talking about minus W 2 u. So, minus W 2 will give me minus Cm cot alpha 2 and plus u. So, then I can write u plus Cm common cot beta 1 minus cot alpha 2, or I can write it in terms of cot beta 2 minus cot alpha 1. What does it mean? It means that I can write R equal to 0.5 plus Cm within bracket cot beta 2 minus cot alpha 1 divided by 2 u, because this definition of R W 1 u minus W 2 u by 2 u is already discussed. So, then we get that in case I want to insist that R has to be 0.5, then this entire expression which is shown here, this entire expression which is shown here has to go to 0. So, this term, this bracketed term has to go to 0, and it can go to 0 only if, following the same logic, if beta 2 equal to alpha 1, or from the second expression beta 1 equal to alpha 2. So, what we get in case of degree of reaction or reaction ratio 0.5 is beta 1 equal to alpha 2 and beta 2 equal to alpha 1. And we can draw the velocity triangles and the enthalpy entropy diagram. First, let us see the enthalpy entropy diagram. We see that H 3 minus H 2, this is exactly same as H 2 minus H 1. So, that the total enthalpy drop H 3 minus H 1 is half of is double of this H 3 minus H 2 or H 2 minus H 1, giving me reaction ratio or degree of reaction as 0.5. And you see that C 3 equal to C 1, the normal condition stage has been assumed, and we get C 3 equal to C 1, which comes out is C 1, which comes in at a stage is C 3, and beta 1 equal to alpha 2 and beta 2 equal to alpha 1, and hence velocity triangles will be symmetric. Please do not confuse these velocity triangles will be symmetric with the symmetric blading assumption that we have talked about earlier. And finally, the special case which you are talking about is R equal to 1. In this case, what we get it is H 3 is equal to H 2, and we can say that R equal to 1 with these expressions in terms of velocity triangles is W u 1 minus W u 2 by 2 u will give me 1 minus Cm by 2 u cot alpha 1 plus cot alpha 2, and hence we get alpha 1 equal to pi minus alpha 2. I suggest that to get a practice, you can draw the velocity triangles and the HS plot for this case as well. Please note, we are talking about R equal to 1. We can extend this discussion from a single stage to multiple stages. I will show you a simple example of typical velocity triangles for 2 row velocity compounded turbine, and I leave it to you to do the other parts. So, first you have to recollect that a velocity compounded turbine, the first stage has a nozzle and the second stage has a stator or the guide blade or the fixed blade. So, the flow is directed from the nozzle into the first stage rotor, and the flow leaves the first stage rotor and goes into the second stage, which is having a stator, and then from the stator it goes to the second stage rotor and leaves. So, we can say that the velocity is defined in terms of mxn. We are now using two subscripts. The first subscript of m talks about the mth stage. For example, if it is stage 1, all of these quantities C, W, etc. will have 1 as the m, and n refers to the pressure and suction sides, which is talking about 2 and 1. So, that means when it enters the rotor it is 2, when it leaves the rotor it is 1. Thus, we have for the first stage for the rotor the velocity can be given as 1 W2 at the inlet relative velocity, and the relative velocity at the exit of the first stage rotor can be given as 1 W1. And similarly, we can talk about 2 W2 and 2 W1 for the second stage rotor respectively. And this is the stage 1, this pink line shows, and the stage 2. And with this I come to the conclusion of today's discussion, which we had on the degree of reactions. We talked about different special cases, starting from the generalized description of degree of reaction in terms of enthalpy and the velocity components, and then we connected and showed what will be the HS plot for different degrees of reaction, in particular for r equal to 0 or the impulse stage or r equal to 0.5. We have talked about the requirements of the velocity triangles, and from there we talked about the requirements of the blades. We talked about the symmetric blading, where we talk about that beta 1 and beta 2 are connected with the relationship that 180 degree minus beta 1 equal to beta 2, and we also talked about the symmetric velocity triangles, where we talked about when we talked about r equal to 0.5. With this I stop, and in the next class we will talk about the few tutorial problems we want to discuss to bring clarity to the discussion we had done so far. Thank you.